Everyone, welcome to our lecture, Physical Base Modeling. We want to finalize today this part, basically the whole Hamiltonian systems, and then we move on to the database part, which is a completely different perspective on systems. Until now, we focus on white box models, so physical understanding, interaction understanding, hierarchical understanding, so how the ingredients work together, all that. And so we have a good understanding of everything. And so where everything common is, if you like, is involved in the Hamiltonian system, where we bring together theoretically the network-based approaches, object two with the integer-based approaches, object three, in one common framework, which is here. Therefore, it's a wonderful theoretical construct, a wonderful theoretical understanding, but also, and this is something I want to point out, or in the middle of the lecture perhaps, that it's also helpful for control design to show you some certain ways how to deal with this kind of systems. We started with a very, very abstract formulation of the entire Hamiltonian system being a set of variables, flows and effort variables, of the external variables, flows and efforts, and the resistive flows and efforts, and then the storages, which are here described by the states and the derivative of the Hamiltonian, have to be included element of the in the direct structure. That's perhaps the most important part. And this is a geometrical perspective. So it's very well adapted to what we know from substitution. In addition, something which also reduces the states, the possibilities are the resistive elements, which also clearly say, okay, not everything is equal. I mean, this is something which you really know to bring it down if this looks a little bit strange. If you remember your lectures on linear electrical networks, and when you solve this, the equations for finding solutions to your network form, you might remember there are two sources of how equations are collected. One are the Kirchhoff's laws and Pauli laws, and second, these resistive equations, which are equations and direct relations which couple some of the variables we introduced. And then you have these differential equations for the inductances and capacitors, and then everything is collected. But these are the two sources, and here you find it as this is a general setting. It's not just by inspection because you did your handwriting and calculated manually. No, this is the general principle of any physical system with non-parameters. And this is an interesting position and an interesting fact. So, however, even if it sounds great and even if it's nice in terms of theoretical understanding, the question is what we do in practice. And then we moved on with the two examples. First, we discovered that if we formulate the system in that sense, we end up with a state-space representation where the matrix A is somehow represented by the interconnection, so it's the Kirchhoff's laws, if you like. And the storages appear in two ways. One, by the derivative of the Hamiltonian on the one hand side, and the derivative of the states here with respect to time. These are the two points which you have to understand. So here, clearly, we see a state of the system is completely defined by storages. There is a theoretical justification for that. And so now air conditioning stopped, as we might hear. This is due to the fact that sometimes things there is no electricity in the room. I don't know why, but it's the best of this. Okay, so This is the theoretical setting. And then we went on to a second example, which is also inspiring from an empirical point of view. It's a DC drive. This DC drive is modeled by means of a simple equivalent circuit, what you know already from other lectures, with the electrical parts being with the electrical parts for the windings, the resistor, the Gauss-Seidel inductance, and the transformation principle into the mechanical part. And then we have the rotating shaft with a certain inertia, J, which has to be respected, so we have to consider Newton's laws as well. So if we do so, and do all the calculations, well, we end up with a system which looks like this. Again, it's a state-space system. Here we find the states as a derivative of this Hamilton function. And A is composed of two parts, which we see clearly in this example. One part, which somehow, due to by inspection, we see here C phi is the transformation value of the transformer of a DC drive, right? So it's somehow the direct structure present there. And second, the second part is the resistive part. And again, so we can say the matrix A is composed of two parts. One is somehow decoding or encoding the computer connection, and the second part is how dissipation takes place. And the question is this a general principle? Can we always formulate this in such a form? And last time we said yes, but under certain conditions, and we have to formulate which conditions are necessary to formulate this. And this is the question of chapter 4. If we say alpha 4 Hamiltonian systems, because we are interested in safe systems, because all of our theory we learned already in control engineering relies on input state output 4 Hamiltonian systems or input safe systems, and we want to see whether this is possible. And this is the guiding example again noted here with the interesting fact. The second fact I want to mention, which makes it interesting, if you look at the inputs here, U0 and M, which is the torque which is applied to the system, and the output I0 and omega. If you multiply the respective variables, so if you build the inner product of U0 and I0 and M and omega, you see is equivalent. Why? Because we have power ports here. That's interesting. And this is something different we should bear in mind. For all Hamiltonian systems, we always choose the inputs and outputs in such a way that the product of which produces power. If you think of the lecture of multi-level control, Professor Kubi, if you ask him, yeah, the name is really nice, I think. I talked to him and he said, yes, it sounds great. Well, there is clearly not power in any case. If you multiply the output variables with the input variables, and at some point he says, well, you can choose the output. Obviously, it's possible that the multiplication of the variables does not yield something like power. So in the general state system, input and output do not relate always to power, but for all Hamiltonian systems, it's the case, and it's something we should respect further. Okay, so one important fact, what can also be seen, and I'll go on to the yellow points here. This matrix J, which is present here, and the matrix R, which is present here, both have some specific properties which we can already inspect. So the matrix J is the interconnection somehow, and R is somehow the dissipation part. Interesting. We can see J is equal to negative of J transpose. So if we transpose J, and do it, if you have transpose J, negative sign is equal. The interesting part, and this has a specific name, the name, if we can transpose a matrix and build a negative of it, it's called skew symmetric. So somehow weird, but symmetric in some sense. It's called skew symmetric. It's a specific matrix form, and R is the interesting second fact. If you remember, R and D are the dissipation constants. They are never negative. So it's a positive definite matrix. Interesting, isn't it? So R and D is positive definite. So the matrix R is positive definite. Something that we can keep in our minds as well. So now we start with the general position. Well, there we know that if we take a fourth Hamiltonian system, and now we have to consider two things. First, the diodes structure of the fourth Hamiltonian system and the resistive part. So we have an interconnection between the diode structure and the resistive part, because some of the variables, efforts, and bills are cancelled out. We know that the diode structure can always, so to start with that, the diode structure can always be represented in input-output relation. Remember, something we did before last time, I think. Can be represented in input-output relation. But now we have also to consider the resistive part, so resistors. And to bring these equations for the resistors into input-output relation, it's necessary that the resistive part can be solved for one variable at least. So we can solve this equation. Remember, we described the nonlinear relation. Where is it? Checking here. The most general description of the resistive part may look like this. It is an implicit form. It's necessary to make this implicit form explicit to have an input-output relation, right? So if we want to make it explicit, well, it's necessary that we can solve for a specific variable, ER or FR, and it's always a sufficient condition for that is that it's linear with respect to these variables, right? It's not necessarily linear in total, but linear with respect to this variable, because then I can solve all these variables, right? It's a simple equation. So we have the sufficient condition here that if it's linear, if the resistive mapping is linear, then we can present everything in this input-output form as before. There is the if. If the matrix is linear, if this the relation, the linear, the resistive part is linear, then we can produce a linear mapping, and then in particular we can write down, and this is the system in this form. We can always write down the system in a J minus R, then the states, and the input is composed of other matrices, and the output is defined as well in the following form. The theory behind it is always the same. So if you want to find this form and want to see the proof, you find it rigorously in the books. But just as an idea, so first of all, a linear resistive part means that Rf of x times Fr plus Re of x times Er is equal to 0, and obviously I can solve for Fr or Vr, right? Because I can invert their respective matrices. This is only possible if Rf or Re are invertible. This is, on the other hand, always possible if we have dissipation, because we have this positive matrices, right, as before. So we need some sort of dissipation. Re times Rf has to be positive definite, and Rf times Re as well. So in these cases, we can say, okay, I can solve this equation for a set of variables, a combination of Er, Fr, whatever that I can solve. Going on, sorry for this full slide. If this is the case, we can further go on and say, okay, this mapping is linear, but it is not completely in the form we had before. So remember, here we have, of course, a linear mapping, yes, of y to x dot and u to y. So we have this linear relation. So k of x times u is y, right? But it's not clear that J and R are represented in that form. The interesting fact is, this is shown here, if such a matrix exists, K, then it can be always represented as any matrix, by the way, as a symmetric and non-symmetric part. And can be split into these two parts, where the skew-symmetric part has this property, and the second part is this one. And here you see the proof for it. It's not that important, believe me. It's true. And with that, we can write out the matrices and say, okay, a skew-symmetric matrix always looks like this. Whatever symbol you take, or maybe J and R, B, Z, or whatever, but we use J and G, and that's it. So the skew-symmetric matrix, again, what means skew-symmetric? Transpose negative of it. If you take this matrix, whatever is inside J and M and G, the negative transpose is the same matrix. It's just by definition. So we can show and say, okay, it's always possible, just written out this linear relation. I wrote the two equations, so make it in that way. So it looks a little bit strange at that point. Here's the mapping, right? So this is one. Here you see the matrices times, and here you see again matrices times u, right? It's exactly that. So with that, you see we can split the linear mapping into these two parts. So in written out, we get exactly this structure. So what we can say, every alternate Newtonian system can be written in this form if the resistive structure is linear in its effort and flow variables. That's it. In other words, we can also say every state space system can be written in the form that the matrix A splits into a skew-symmetric part and a resistive part. That's interesting. So we can always differentiate between the things which are responsible for connecting the entire system and everything which is responsible for dissipation. Unfortunately, that's perhaps a problem, or even more complex. It's not that easy to discover the network. So something like the adjacency matrix Have you ever heard of the adjacency matrix? Yes, for network descriptions, which point is connected to what, and you put the one in there for negative of it. And the zero if it's not connected. So you compile a network which you draw into a matrix by just saying 1, 0, 1, 0, and with that you can connect or display a network in forms of a matrix. This is unfortunately not easily seen in J, for example, because the network structure should be somehow present. Unfortunately, it's not like this. But we get more structure. More structure is always helpful. Okay. In addition, if you look at this input-output relation, we presented for the diac structure, and together with the input-output relation for the resistive part, we end up with the fundamental power balance equation, which says that if we look at the multiplication of the external influences, so sources, efforts and flows multiplied plus the inputs multiplied with the outputs, we end up with the following structure. If we do so, we find out that it's always dissipating. So it's always everything which goes in goes either out, but it's nothing produced inside such a full Hamiltonian system. That's an important fact. No? So it's either stored or dissipated, nothing more. So everything which is going in goes out, and that can be seen here. And this is one of the fundamental facts why these kind of systems, these kind of descriptions are helpful, because with that you can describe, for example, stability and such things. I want to show you this in a second. Okay, but up to now it's just a description of the system. So in many cases we can say some of the parts are missing. This is, for example, the definition of an input, states, output, post-Hamiltonian system without the exclude, which very often applies to practical examples. There you end up with the state x dot is equal to j minus r times the state variables plus gu, and the output is super compiled. So g transpose times the states, and that's in linear setting. Here we have the most general one. It's a non-linear setting. Well, it's a non-linear system. What we see here, because it depends on the state, is the typical system description which we find in non-linear systems. In a linear version, these matrices here are constant. G is constant, and G is constant here as well. And here we find the state. So it's as simple as that. The inspiring fact is it gives us an additional structure. It explains why we have the states as states in the system. What is building the states? So the answer is given to the very beginning starting point to say, well, the state is something which is capable to predict the system behavior. Now we know what is the physical ingredient in it. It's energy. Here we see it. And energy is somehow connected via these two things, and J and I. That's it. Okay. Some more notes with regard to that. I just want to highlight that this in particular. So again, just to show you this source of this particular example. Here you see an electrical system or an equivalent circuit of a hydraulic system or whatever you like. But I think of an electrical system right now, and this electrical system has a voltage source here, a resistor, and a second resistor, another one, a capacitor, and an inductance in between. And We want to build on the Port Hamiltonian system here and show that it applies as well what we have seen before. So let's do the job. We try to write down the various variables. So we start with the inductor first, which is h of xl is equal to 1 over 2l times xl squared, where we define xl dot being psi dot being ul. And in addition, we know that dh derived with respect to xl gives 1 over l times psi, which is nothing else than IL. So the current through the inductor, right? The second source of states is the capacitor, which we find here. And remember, we use the thermodynamic framework. H of xc is 1 over 2c xc squared. And with xc defined dot as being the q dot, being IC, it's the current through the capacitor. And again, we can formulate our states. The HDXC is 1 over CQ, which is UC, so the capacitor voltage, nothing more. Okay, in addition, we have energy dissipation, which is given here, which is URI for all the resistors, gives a nicely linear relation for the various currents, IRI, so, and I is equal to 1, 2, and 3, because we have 3 resistors, and all follow Ohm's law, okay? So that's it. In addition, we have 4 junctions, the spanning trees, 4 junctions. We have nodal equations and loop equations, and now we have to discover which one. In our network, so perhaps you have 4 junctions. But just 2 necessary variables to describe the system, right? If you think of the spanning tree situation, we just need 2 variables to describe the entire system. Okay. Okay, now let's write it out. We can say, okay, the 4 junctions I want to write out, because the 4 junctions describe the or one relation. So we have the was IR1, and we have U0, which is equal to UR1, second junction, R1, IR1. So we get on the slide still I0 is equal to IL plus 1 over R1 U0. This is the first. Next, we can write down the output equation. Let's start with that, which you might find now. It may look like this, which is I0 equal to dH dxL plus 1 over R1 U0. So in matrix notation, 1, 0. And here we have the states dH dxL and dH dx C with H being the summation of all energies, xL squared plus 1 over 2c xc squared. And now we go on. We can calculate the voltage drop over the resistor R3 right inside, remember? And look what happens with that. Gives another consider the following: UR3, which is equal to R3 times IR3, which, by the way, is R3 IC, which again is, and here comes the R3, sorry, IL minus IR2. Again, one junction which is used, or even R3 times IL minus 1, IL 1 over R2 multiplied with UR2. And UR2, again, we can use junction information R3. Sorry, I just want to show the various steps to reach the final position. Is IL minus 1 over R2. We use a loop equation to show that this is equal to UR3 plus UC. Now, UR3 is given. As you see, you can solve for UR3, right? You have UR3 on both sides. You can solve for it, and we get a very interesting result. So UR3 is given as, and now this is nothing surprising. This one, and now IL minus 1 over R2 times UC. Okay, so this is something we would have realized also by ourselves if we look at the parallel connection of the different branches of the circuit, and here it comes out of the equations directly. Okay, now we do the very same for UL. Oops, not so much space left. Sorry for that. Same for UL. We do it that way. Sorry. Here we are. Want to have a white screen. Okay. So Same for UL. So we get, which is equal to XL dot, which again is equal to U0 minus UC minus UR3, which again shows that we are using junction information. So we get XL dot being equal to U0 minus R2 R3 divided by R2 plus R3 times IL minus R2 divided by R2 plus R3 times UC. And this here, this is equal to the derivative of the Hamilton function with respect to XL. And this here is equal to the derivative of H with respect to XC. Okay. Same way, XC dot, we compose everything, we end up with R2 divided by R2 plus R3, EH dXL minus 1 over R2 R3, sorry, plus R3 EH dXC. So now I want to compile everything. We end up with the system dynamics XL XC dot is equal to minus R2 R3 divided by R2 plus R3 and minus R2 divided by R2 plus R3. And then we have R2 divided by R2 plus R3 and minus 1 over R2 plus R3 multiplied with EH dXL, EH dXC plus, minus the 1, 0 times U0. This is the state space equation, as you see. Now, just combine everything together. So what did I do? I used the Noble equation, I used the loop equations, I used the linear resistive elements to solve for the various equations. Second, I described the Hamilton function, the energy of the storages, and that used the thermodynamic framework, so to set these state equations, the states, and then I end up with this. It's just mathematical manipulation. So if I do everything I did before by hand, you do it then that way. If you like to do it more systematically, then I show you on the slides. You don't have to do many calculations. It's can be fully scripted in a computer algebra tool. That's the answer. So what is missing still is the output equation. I don't want to write it down because the output equation has been already set one slide before. Okay. So, and again, if you look at the various ports, if you multiply the inputs U0 with the corresponding output, you again see that it's power preserving or dissipating. Same thing as before. Okay. Now, well, what I did here seems, well, it's a tedious calculation, obviously. It's takes time and so on. So the question appears, why not doing this automatically? Is it possible to deduce from every given the equivalent circuits or block graph a post-Hamiltonian system automatically? And the answer is yes. Fortunately, you can believe me, yes, it's possible, and the question appears, okay, we see it's not always possible because we need this linear resistive structure, we need something to solve for, and there are some intermediate steps which need some careful attention. But obviously, more or less, there are steps where I said, yes, there exists something like a skew-symmetric matrix. There exists something like we can solve for. This is always nice mathematics, but unfortunately not very constructive because at the very end of mathematical calculations. And with that, we ended, I would say 7 years ago, to bring this in a practical setting because we as you know, I mentioned it here a couple of times already, we try to build new control strategies for combined energy systems. So energy systems including heat, gas, electricity, and then such a overall description is very helpful. So we started with the question: is it possible to represent such a system? In addition, we see something nice later on, such direct structures, in particular post-Hamiltonian systems, obey a certain wonderful property because if you connect direct structures, you get again a direct structure. And so we can compose subsystems out of subsystems and build again a super system easily. So for us, it was a possibility to build building blocks for building controls at the very end. To build huge, super huge systems. If you think of the electrical grid, it's a super huge system. And if you want to write down the differential equations for everything, it seems to be a little bit problematic. This is still possible, but if you want to build control strategies around a system with millions of states, it's perhaps a little bit problematic. And therefore, our attempt was, well, why not using a hierarchical modeling paradigm, which helps us to compile this electrical system and later also the hydraulics and for district heat system and the gas network. And there the question appears, well, it's highly necessary to have a tool which does it automatically for the individual parts. And then we realized, yes, nice, that literature just says that there exists something like this input-output relation. It never tells you for your system how to build these things. And this is really frustrating for engineers because they want to build something. And we started with this point and read the wonderful literature there, and we were aware of it. But we did not found anything constructive. Constructive means that we can really graph these equations and for control design. And there a huge mistake discussed. This is the typical point where I realized might be difficult, and there are substantial theoretical questions behind and practical questions behind the typical engineering which leads to this. And this is something which we see here. First of all, the question is, yeah, it's resistive, it's linear, then we have a sufficient condition. Is there a necessary condition also? No, unfortunately, until since 3 years ago, we found something like a necessary condition also, under which condition we can build these things. And in addition, it's possible to build something like an automatic tool which allows to build Port Hamiltonian systems out of a bond graph. And this is wonderful because you can compile a huge system. And the bond graph, why a bond graph? Because a bond graph is the natural starting point for anything in modeling systems using, for example, Dynalar, Euler, or whatever SimScape. You can everything compile into a bond graph. So for us, was the natural language at that point, because the language using this kind of non-singular flow but non-causal modeling relies on the bond graph structure. So it's possible to transfer everything from these tools to a bond graph. And this was our idea. We have a real system, a bond graph representation is possible, and then there exists a tool which is called Amoto. It's due to automatic modeling tool, and in addition, we could use something where we completely automatically can design observers with this, so observe states in the system. And this was implemented later in the structure. It's not so difficult to see the different steps because of what we did. We have a bond graph. We look at the diagram structure. We make this diagram structure implicit first. Yes, because if you look at the bond graph, it's first an implicit diagram structure as before. Then we compile these different diagram structures of different subsystems which are connected to one implicit diagram structure. This diagram structure can be made explicit under some conditions, and the PhD student found out under which condition this is possible and can say, no, it will be never possible to build a PHS out of your system modeling paradigm. It's interesting. You can say no, it won't be possible. And then you can build the explicit PHS and transport it to everywhere, matter, tech, and whatever you like. And can further use it with mathematical. So later on can put it into your computer-aided engineering tool chain. So this is something Mr. Giesler will show you perhaps in one of his exercise lectures. And you can use it, it's freely available. So you can play around a little bit with it, and you start entering such kind of bond graph. And here is our example. There you see the bond graph. Perhaps for homework, try to transport this into a bond graph. Typical question, by the way, for the oral exam. Given a system, I want to see a bond graph out of this. Would be something like that. And here you see the result, and everything I did by hand was calculated on 3D also. Okay. Now, this is additional material for 5 in some parts. One part is I want to first highlight some properties of the Port Hamiltonian systems. One, the input state output Port Hamiltonian systems, ISO PHS, are a particular subclass of state space system. Why? Because we have the combination of input and output in such a way that they always produce power. This must not be the case for a state space system. Remember that. That's important. It's really a subclass. So as for comparison, if you remember any nonlinear system in explicit form, you end up with x dot is equal to f of x and q. In addition to that, we know that these nonlinear systems obey a certain structure, and this structure is composed of a skew symmetric part and a dissipation part, which is helpful later on. The variables which govern the system are compiled out of, namely the states are compiled of the storage function, so the Hamiltonian. So we have this kind of relation. And the system is governed by a very famous and important power balance, because if we do the derivative of the energy of the system with respect to time, not with respect to the states, be careful, then we see that everything transported in and out of the system is either stored or dissipated. This is what is meant with here. And this is a fundamental fact. Okay, first, something I mentioned here, I just want to go into detail because it's not that important. It's just a fact for you to keep in mind. If I have one diagonal structure, another diagonal structure, and two systems basically, if we have two different subsystems and we connect them via two ports, via, for example, a transformer or something, then the question is what happens if you connect them? So two diagonal structures, and there's a junction in between, and we want to know what results. The interesting fact is the interconnection of PHS again gives a PHS. That's the wonderful fact. And the main ingredient of that is that you have to look at the different diagonal structure and see that again in diagonal structure results for an engineer it sounds clear because you have one diagonal structure, you have another diagonal structure, and you put a junction in between. What should happen? There is nothing else but from a mathematical point of view, if you want to really precise, the signs have to be looked at. Why? Usually, the diagonal structure, the signs point into the diagonal structure. So every bonds point into the diagonal structure. That's our definition. So we have a certain sign convention for both diagonal structure. So there is a certain misconception at that point if you put the junction here. And you have to check for what happens for the integrated diagonal structure. But this can be done. And the interesting fact is if you combine two systems, the overall system Hamiltonian is just the addition of the different Hamiltonians. This is perhaps also not surprising because where the additional energy storage come from, then from the different subsystems. So for us, it was the natural starting point for dealing with energy system in that way. This went very well in that direction. Okay, second, and this is additional material, nothing for our lecture because it doesn't have to do with modeling. If there is something which you see there is some sort of dissipation, then we see some properties with which we can prove stability of the system. That's, by the way, the reason why post-Hamiltonian system started to be researched for decades ago. Because one wanted to treat nonlinear system stability in a more practical way. And the interesting fact here is, first I introduced one just a question for my information. Is there somebody hearing the nonlinear control section? Are you already in the part when you hear something about the Markov stability? Okay. Okay. Now I can check for the moment. The question is, do you remember what Lyapunov says? Yeah, what says Lyapunov? So roughly speaking, so overall.
If this resting state is stable, then there is a border, so to speak, where the where any state is going into the resting state.
Yes. Something else? There is such a famous function V, which is used to prove that.
Yes,
Check one of the slides, right? Hey, it's okay, it's okay. We're collected. So, what Mr. Kubi said, just I asked the others, perhaps you have an idea. Do you want to mention that? What he said? No?
Yeah, as far as I know, is the replacement function for the system, so you don't have to evaluate the energies into the system, but we have to have the same properties as the energy.
Exactly. So it is motivated. So the Lyapunov theory is motivated as follows: if a system is stable, then there might be some sort of energy, I should say, which is reduced over time. So the energy level of the entire system, if it's stable, should be reduced. This is the starting point for Lyapunov theory. And Lyapunov realized, well, perhaps the natural energies of the system are not very well suited for proving that. It is sufficient to show that something which looks like energy reduces over time. That's the basic idea, right? It must not be energy. In many cases, the energy function is not a bad idea, and therefore no function by the way. So if you want to prove that, and if you sit in front of that, usually in the exam, by the way, at least from my side for the non exam, usually the Lyapunov function is given and for your purpose, because otherwise, in other cases, you sit weeks, months, years to find the Lyapunov function, because that's the main problem for this theory. And I know Mr. Kubi said this to you that finding V is really, really a tough problem. But here is an idea. Here we have the same situation. The energy is somehow describing the entire system, right? So if we have the energy dissipation property, then there might be something that everything which goes in goes out, and then we should have a certain sort of connection between Lyapunov and this power balance, right? And I skipped some slides, and I want to put this in the following setting. Here's the Lyapunov theory. If you have an autonomous system, x bar is equal to f of x, and you ask the question whether the trajectories x go to the point zero, to the origin. Then you can prove this if there is some positive definite function, the Lyapunov function, usually called v, and a v. With the following properties, it must be always v of x must be positive, but v dot with respect to time, so the dt is always negative. That's interesting. If it's negative, then everything goes down to zero. Okay, right. But the only thing you can prove is, or what you can prove is that the trajectories reach the origin. It's stable. So like a pendulum, you leave it here. If it's weak and left, my pendulum, it will oscillate from left to right to left to right. You will never find something like that. It will not go to the origin. If you have friction, the amplitude will reduce, and here's the origin, right? For this point, this will never work. Because if we will not find something like the Lyapunov function, because if I smash against it, it will fall down. So, on the other hand, what we have for Hamiltonian system, left-hand side, we don't have just a system x dot is equal to f of x. No, we have a system x dot is equal to f of x and u. So we have inputs, important, and we have outputs. But there is a similar relation. First, again, we have a storage function, S. which in our case corresponds to H. And the derivative of H is smaller or equal of the value of U transpose Y. So everything which is at the port to the system, Y is the output, U is the input times output, R is the port of power transported into or out of the system. So we can say if this holds, we can prove everything is dissipated or stored. So it's some certain notion of energy balance. Now let's make the following assumption just to connect this to your nonlinear knowledge. Suppose U is always 0. What happens? Here on the left-hand side. If you enter U equal to 0, then you have an autonomous system, right? It's 0, x dot is equal to f of x. Yeah, right? Y is not so important. The only thing which is important is that one. U equal to 0 times y is 0. Oh, wonderful. The Lyapunov theory appears, right? So, not seen? Because you're, yes, no, yes, okay. So that's interesting. So what we here see is a so-called dissipativity theory, which is closely linked but not equal to the Lyapunov theory or the nonlinear relationship. So there's a connection to the Lyapunov theory. What is important? Dissipativity theory, something that tells you something about the input-output relation and stability, because it dissipates or stores. And on the other hand, if there is no input, U equals to 0, for example, then you can prove then you have the Lyapunov theory, right? So now you see why we are talking about four-Hamiltonian system for energy systems, for example. Now our idea, and it worked out, so I can say it's a good it's a happy end at that point. If you have an energy system with hundreds and millions of participants first, and if you connect them, then one problem is the stability of the entire system, right? That's a problem which we have today. That's why you are charged with network costs right now. If you look at your bill, unfortunately, the network costs raised over time exponentially since the last 10 years. So it looks like this, and as you know, at the very beginning, everybody thinks an exponential function is a linear function, but at the very end, everybody realizes, oh, it becomes problematic, and that's the point we are right now, because really we are in the steeper slope part. That's something which is happening, and this is due to different facts. But one fact is we have volatility in the energy system, and we have this interconnection of the different systems, and we have really a bad, I should say this as a control engineer, energy system, because it stems from the times in the 60s and 50s, where we have just these nuclear power plants, coal-fired power plants, and so on, and just a few. And this worked out well. Okay, I won't say anything against it. It's wonderful, but now with millions of participants, which in addition to that, if you remember your energy lectures, or lectures on power electronics and so in the past, you can say, I just have peak control, and peak control doesn't change anything. Nobody sees those. But now every converter, every AC DC converter enters storages like the intermediate capacity. So we have always integral parts in it. This brings substantial stability performance to the system. So back to my question. Suppose you have an energy system with millions of participants bringing in their own integral control. By the way, you can check this. If you like to do electronics, take a V 5 volts voltage stabilizer, which stabilizes. Take a 12 volt battery, and then you try to stabilize 5 volts. And you take a second, if you connect them, then you can see one split. You can do this at home, before it heats up and then it splits at the very end. One of them. This is an instability form. So just by empirical evidence, you can check it from. No water for fire extinguishing. Back to our problem. So a couple of these millions integral control strategies connected together. Our idea was, well, if it's possible to describe the entire system as a Force-Hamiltonian system, then we have this, each part can be described as a Force-Hamiltonian system. So your AC-DC converter or your rooftop PV, my AC-DC converter for my rooftop PV, the wind mill over there, also an DC-AC converter, sorry. And if every part can be described by a Force-Hamiltonian system, then we naturally get this one. And so the question appears, if this is the case, can we prove stability for such a kind of a system if they interconnect? And the reason why we believe that this would happen is due to the wonderful property of direct structures, because if we interconnect the direct structure, we get again direct structure. So we can hope for something which proves that. Well, this was the initial idea. We're still on the way. The first proofs, we can show this for a specific classical system that this works out. So you can connect everything with ring and sail without under certain design conditions for the controls. So, and there you see that you can really do practical things with theory at that point, right? For the theory, and this is connected to stability, as you see on the right-hand side, the different versions of it. Okay, so that's what I wanted to say here. Some outlook. Of course, you can do control with Force-Hamiltonian systems. This is given by the outlook. Perhaps interesting for you. You can try to associate a certain kind of control strategy to Force-Hamiltonian system, but this is in the story. It's nothing for our modeling class here. It's something for nonlinear control engineering. It's interesting because it directly starts with the Force-Hamiltonian system and asks, what do I have to do if a system is given and I want to control this and I have this structure and I can use this structure. And there are some ideas here on the next slide. I don't want to present them because we already released with regard to our lecture. Okay, so now to sum this up. To sum this up, first, I want to highlight two things. The most important practical parts are the network paradigm and the energy modeling, the variation principle. These are the ingredients with which I build systems today. It depends a little bit on the system, what I use. If I have a new system, if I need interconnected structure, I very often rely on the network paradigm. If I want to build integrated multi Energy systems, for example, multi-domain system, I very often use the variation approach because it's very helpful to combine different domains. As mentioned before, so this Sphere platform last time, right, where we have these different aspects, makes it, well, you get easily the differential equations. Chapter 2, 3, practical experience. The main topic for you is to manipulate a couple of systems and to try and to work with that and to get a little bit more familiar with the different mutations and so on, and to understand principles. Here in chapter 4, we try to generalize the things a little bit. So my intention was not to bring up a completely new theory because it just fused together all the things before. So it gives a little bit more insight on what systems are, how they work together, what kind of general properties do we get. That's the topic of this one. And it's perhaps, and that's my last message, or key takeaway, is perhaps the starting point for something inspiring, like new control strategies. So if you're interested in, well, doing this complex control, because today, if you think of today's problems, if you think, for example, of the electrical energy system, well, it's a huge system, it's network, it's, not everybody knows everything, that's something which is also important. It's something completely different to a car. If you look in a car, well, there might be possibilities that there's some person who will find some person who are capable to describe the driving dynamics entirely. They can write down the equations, you can ask them, they are the super experts, etc. This is existing. But if you think of huge network systems, might be also network system for chemical engineering. So then you have the very same situation. Or a district heating, whatever you like, then they become overly complex, and it's not easy to find somebody who is capable to represent everything in this head. And so we have a combination. So you need something which deals with these different entities, and this is a new perspective. That's what I wanted to show, that there is a close connection to what we are doing right now in research, but also where are the problems in practical examples. We are driven by practical examples. Okay. This is the white box perspective. So again, as a summary, a white box perspective always tries to generate insights into the system. So we should understand everything. We should understand the interconnections. We should understand the data flows. We should understand how, you will see it, power flows from A to B. Well, is this a good assumption in practice? No, unfortunately, because in many cases, we don't know everything. We have problems in describing it, and there might be we might have difficulties to find even the physical laws in mind. One example where I think it's very where I think it's very clear, if you try to describe, for example, the dynamics of how humans are entering a street crossing in India. You ever seen these pictures trying to cross the streets without rules? Not every street is without rules, I don't want to say that. But if you want to understand the principles behind that, it's difficult. Now think it's difficult. So there exist some principles, but there is nothing really generalizable. So if you want to build white box models of how the cars should drive over such a street crossing, it's difficult. You won't find something in that direction. So basically, the question is, what can we do then if we want to build autonomous driving cars in such situations? If we do not understand how the environment behaves, or other situations, very famous for me is battery technology at the very beginning, early ages of this driving fuel cells, for example. We did not know how to describe it from the dynamics, from the resistive parts, etc. Now we moved on in theory here with material science, but at the very beginning, if we do not know anything, then we have problems with this white box approach. This is one part. The second, of course, is that we do not know perhaps some parameters. A typical example for me is automotive engineering example. If you build a car, usually you should assume that the weight of the car should be clearly can be calculated. Why? Because you make a computer-aided design of the car, you know the materials, everything, and then you just sum up all the materials, and then you have the list of materials, and you get the weight of the car. Well, this weight of the car is really important if you do, for example, driving dynamics, because the mass of the car is important if you want to reduce yaw angles or so. But during my professional career, when I sat in a car and get a test car, for example, to do the control engineering, I always realized the weight indicated in the database is not exactly the weight the car has. Why? Well, because somebody implemented something inside, they realized, yes, it's necessary to put some foam inside and there are additional materials. So I never had the car weight, which was calculated out of the database computer design. So this is a simple example we can manage with twins, etc., and be professional, etc. But I just want to highlight that there are some situations where you do not know the parameters, and you should infer them from data. What did I do? The simplistic car example, like I weigh the car every time I went on the test track. At the very beginning of my day, I determined the weight of the car by weighing it. That's at the beginning, and the same is by the way true for the various inertia values. But this is a little bit more difficult because you need a pendulum, for example, to pendulum the car. But it's also done to describe that. Okay, so I just want to motivate the fact that sometimes it's not possible, or sometimes it's difficult to get models from first principles, right? And this is the starting point of our story of the next chapters, which lie ahead of us if everything is starting up here. There we are. And I have to be careful to show you that. And we have two perspectives on it. First, we start with so-called discrete time approaches, where we have where the data is represented in discrete time, just at some instances, not in continuous time. And then we move on to continuous time approaches later on. So, what is our aim? We want to have we want to understand the characteristics of database modeling, basic theory, of course, behind it, for static and dynamic systems, we learned the most important method, the instrumental variables method, which is part of our lecture here. And we describe the procedures and some connection to neural networks. I should want to say that we won't treat neural networks entirely. It's a really huge topic, but I just want to say, okay, there is a connection to it in some sense. Okay. So first, I want to start with this picture, which you might remember from white box modeling at the very beginning. What is the difference in the procedure from black box to white box? Well, we leave all the steps out, which gives physical insights. So idealization will not be present, obviously. Mathematical functions will not be present in the sense that we use physical laws or something. This is omitted. On the other hand, of course, you have to define the system which you want to inspect. So the first delimitation step is necessary, obviously. You need to define the inputs and outputs of the system. You have to define, yes, I want to look at the bicycle and not at the gun. That's also, so it seems funny, but it's important. This is the basic structure. So we leave 2 and 3 out, but we always start with some model assumptions, and that's the difference. We have a model structure with 3 parameters without any physical interpretation. This is the pure form of black box modeling. And perhaps I should highlight this. Oops. I should highlight this. We don't have any physical interpretation here at the very beginning. And then the only our work to do is we have to calculate and determine the parameters of this kind of models. And then we get a quantitative model, and sometimes we simplify the model again, but usually the last step is left out. So just to sum up, what we did that before, here are some pros and cons. Of course, the pros, no understanding of physics is necessary. This is a pro, but also a con. Depends on your situation, right? So, and that's my point. If you talk to data specialists, they always have data methods are the best. If you talk to the traditional control engineering community, white box models are the best, and the truth is in between, right? And in your generation, should not just learn one side, should understand both. And both sides are necessary to do the right thing in the right situation, because sometimes it's easier to build a white box model and then you use it, and you get easier results. Sometimes it's exactly the opposite. It's wrong to use white box models because it takes too long, it takes time, it's difficult, etc., all these things. And you should rely on black box models. I want to give one important point. The real world is now described by data. That's the important difference. So we associate the real world by measurements. It seems trivial, but the starting point for this problem is you need data. And if data is not available, you can't do the methods. And this is sometimes the most important part. That's why these black box models are always present in situations where the data is always available, right? So if you think of these database strategies for the internet companies, they have data because you need your data to them for free, unfortunately. My personal perspective. Because it's your data. But in other situations, data is not available. I want to give one example where it's quite clear. If you think of, for example, on medical modeling of the human, and you want to model diseases. Now, it's clear for some of the diseases, there might be the situation that you have a lot of them. For example, skin cancer. You have a lot of features, and you can just try it, and it works really well to find out, yes, there is a problem, for example, better than a medical doctor. So, there the data is there. But if you have a disease which exists only one every 1 million patients, you don't have the data. Sometimes that is trivial and clear, but sometimes it's the situation you don't have the data because you have to generate. This is the typical situation, for example, in automotive engineering. The data is not present for this specific part or this specific model. For example, we want to model the steering column in the database, right? Data is not present. You have to do measurements. Measurements can only be done if the physical object is there. In simultaneous engineering, the physical object is often not there, which will exist. So what we need is very often a test bench. So the story starts very often up front of this problem. Here, the rest of the part is easy. I don't want to say it's easy because it's still research in some parts, but from a practical engineering point of view, project management, you have to go months before and start to build a test bench, for example, to generate the data. For example, therefore important. Now we want to look what we can do in our chapter here. And there are basically different models we want to, which are possible, but we just want to look at so-called supervised modeling. So the important aspect is that we have labeled data sets to fit models to the data. There is some sort of mapping, which is important. And our aim is to adjust three parameters so that the input-output relation fits very well. That's it. And that's the story of our chapter. And we start with that tomorrow, I think. Have a good day. Bye-bye.